This is section 9.3, the integral test and P-series test. We've learned two other tests, geometric series tests and the nth term test for divergence. So this section has two more tests. Let's get started. The two bullets are basically the two different tests, the integral tests and the P-series tests. They also mention the harmonic series. Harmonic series is a P-series. We'll get to that. All right. So this is the integral test. Basically, what they've done here is they've taken the sequence, write it as a function, and then do an improper integral from 1 to infinity. As long as the function is continuous, positive, and decreasing, this works. So a function that hops back and forth between positive and negative will not work using the integral test. Okay. Now, here's the case. If the integral converges, then the sequence will converge, or the series will converge. If the integral diverges, then the series will diverge. Now, what it does not tell us is what the actual convergence value is. Like if the improper integral converges to 1, that does not mean the series converges to 1. We just know that it converges. You look at the first example. Actually, we can't use the first example because this will require inverse trig. All right, so I'm going to change it to this one. All right, so what we need to do, well, let's first of all, we know this is 1 over x squared. It is always positive, right? And it is always decreasing. If you take the derivative of 1 over x squared, it would be negative 2 over x cubed, so it's constantly decreasing. Remember, x is this. We're looking at x greater than or equal to 1, so it'll be constantly decreasing. All right, and it's continuous after n equals 1 or x equals 1, either case. So we make this integral. We convert it to a limit. We let b go to infinity. We integrate this, and we get negative 1 over x. Substitute the values, we get negative 1 over b plus 1 over 1, right? That plus comes from doing minus a negative. All right, now we take the limit as b goes to infinity. This term is going to 0. Remember, when the numerator is constant and the denominator is growing infinitely large, that is 0, and that's 1. So the limit is 1. So the improper integral converges to 1. So that tells us that the series converges, but we don't know what it converges to. It has to be less than 1, because remember, this is a discrete set, while the 1 over x squared is a continuous area. All right, so that's the example. Let's look at P series now. P series looks like this. The n, the variable, is the base, and the exponent is constant. Okay, so the base is n, base varies, but the exponent is constant. All right, now that's the P series. The harmonic series is this one. So basically, harmonic series is when p equals 1. Now this is the convergence of P series. If p, the exponent, is greater than 1, it converges. If the exponent is between 0 and 1, it diverges, right, including 1. So the harmonic series diverges. The transition was not edited. I made a mistake on the slide, so I had to fix it. So if there's a weird transition between the last slide and this, that's the reason. All right. Example 3, convergent and divergent series. We're going to look at convergence or divergence of the harmonic series and the P series with p equals 2. Harmonic series. This is just a reminder of what that theorem says. Harmonic series looks like this, 1 over n. Here, the exponent is 1. So, according to this, because p equals 1, it diverges. Let's look at the P series of p equals 2. P series of p equals 2 looks like this. The exponent is 2. That was the example I used for the integral test. That's probably why the author didn't use this example for the integral test, right? Because it's better done with the P series test. Right, up p equals 2, which is bigger than 1, so it converges. That's it. So the P series test is very easy if it's in that form. Let's look at another example. Well, this is not a p-series, right? This is not n with an exponent. This has a log in it, so this is not a p-series. So the other test in this section is the integral test. I rewrite it as a function, and this actually should look familiar to you. We've done this integral several times. It comes out to be natural log of x. If you've forgotten how this is done, the integral of natural log of x is 1 over x. So the derivative of the denominator, not counting this x, is right here, 1 over x. The derivative of natural log of x is 1 over x. Natural log of x has an exponent of 1 in the denominator, so it's the natural log of the denominator, so it's natural log of x. We substitute the b, and this is what we get. So as b goes to infinity, this expression is going to go to infinity. So the whole expression is going to infinity. Alright, so what does that mean? So what? That means it diverges. That's it. By the integral test, this series diverges. And that's about it. In this video, we had the integral test. If the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. We don't know what it converges to, if it converges, but we know it converges. That's all that matters, right? And most of these tests are like that. We're usually not going to know what it converges to. We might be able to approximate it, but we're usually not going to know what the series converges to. P-series test. It has this form. It's the variable is the base. The exponent is constant, right? And if p is greater than 1, then the series converges. If the p is between 0 and 1, including 1, then the series diverges. So those are two tests. P-series is pretty straightforward. It's usually used as a background, as a stepping stone to prove something else. Okay, because it's pretty straightforward. All right. And we could just assume things like 1 over n cubed converges. And you don't have to say much. You could just say it because it's a p-series and the exponent is 3, so it converges. Alright, but anyway, that's the end of this video. That's a pretty short section, and that's it for tonight.